Assalamu alaikum and welcome to lecture number 21. In this lecture we are going to discuss about the another representation, that is block diagram representation of LTI systems, and we will also talk about the response of LTI system to complex exponentials. Block diagram representation of LTI system. It is an interconnection of elementary elements, and it is more detailed representation of LTI system than the impulse response or the difference or differential equation. This describes how the system's internal computations or operations are ordered. For example, we have a discrete time system represented by the equation y of n plus a y of n minus 1 equals to bx. So if we look at this equation, the operation involved are addition, multiplication by coefficient or scalar, that is we have bx, b and a. So these are the scalar multiplication, or we can also call them multiplication by a coefficient, and there is also delay involved in this equation. So to represent it in the block diagram, first we write it in the recursive format, that is we write output on the one side and inputs and the previous value of the output on the other side. So we have three operations involved here, that is scalar uh, uh, multiplication, which is b, and another scalar multiplication, which is a. So and addition. So to represent addition of the two signal, we represent the circle with plus sign inside. So this is to represent the addition. So x1 multiplied by x2, for example, we have. So this is represented by block diagram as here. Then another operation is the scalar multiplication. So we can represent the scalar multiplication by an arrow as shown here, and the third operation is delay, which is represented by this block. So y of n, this is the output, and output equals to b times the x of n. So this x of n, here we represent the scalar multiplication, and then we have minus a y of n minus 1. So n minus 1 represents 1 unit delay, so we write it like y of n. This is y of n. So if I delay it by 1 unit, I can represent it d, and I can write, because it's a single element, so it's a delay by 1 unit. Again, we have scaling of the delayed output, so we represent scalar multiplication by an arrow. So here I put a minus minus a, so this becomes minus a times the y minus n. So this is how we represent the recursive equation, this one, using the block diagram. So this is the final representation for this equation. So we can also have another type of problem where we are given the block diagram and we have to write the difference or differential equation. This, I think, quite simple problem, so quite simple topic, so I will not spend much time on it. So for example, another system we have is this represented by this differential equation, which is here. So in this equation we can easily see that we have three operations involved here, that is addition, and we have scalar multiplication or multiplication by a coefficient, which is b and A, similar to what we had in the case of discrete time system. And the third operation involved is the integration, multiplication. So we can write it like this. Now to solve this problem, again we rewrite the equation so that we have output on the one side, which is y of t, and the other quantities on the output on the left side, and the other quantities involved in the on the right hand side, right? So again we have the addition, so similar to what we had for discrete time, continuous time, it is also represented in the same way, with the exception that now independent variable is t. So similar is this one. And for d, in continuous time case, we have the differentiation, so we represent differentiation by a block inside d and it, right? So to solve this equation, we can write x of t, okay, multiply by b by a. So this is the input, then we have the output y of t, and we are taking the differentiation or derivative of the output, so we represent it by the block d. So after this block we obtain dy by d of t, because at this point we have y of t. So you understand this y of t, so if I differentiate it, I get dy t by dt. Now again, if we look at the equation, so in equation we have the scaling factor, which is -1 by a, so this is how we represent the scaling. So although we have solved this using the block diagram representation and right, but differentiators have some problems. They are difficult to implement, and they are extremely sensitive to errors and noise, because a small variation, you understand, will result into big variation if we take the derivative. So alternate representation for the this one will be using the integration. So if I take the derivative of this equation, I get y of t equals to, you understand that we can represent it like, let me write it. So if I take the integration of both sides of this equation, it will result into something like this. And now we get rid of the derivative. So specifically, if we assume that the value of y is y of y at minus infinity, if this is equal to 0, then the integration of dy upon dt from minus infinity up to 2 is respectively y of t, and consequently we obtain this equation. So it's most widely used. So for the integration, we simply write inside the block the integration symbol. So if x of t is input, then derivative integration of this will be represented by block diagram as shown here, and we have the limits for integration from minus infinity up to t. So I think quite straightforward. So this is one of the homework problem. You are given a block diagram and you have to find the uh, differential equation. So here the block diagram representation is for discrete time system. So you have to find the difference equation for this block diagram. The answer is provided here, so I hope all of you will go through it, and using the block diagram you can find the difference equation for this one. So we start a new topic, a new chapter, that is right. In the previous chapter of LTI, we represented discrete time and continuous time signals as scaled and shifted impulses, and by knowing the impulse response we can find the output of the system using the convolution sum or the convolution integral. In this chapter we are going to explore an alternate representation for the signals and LTI system, where if we can represent the signal as a linear combination of complex exponentials. So let's start with the simple example that we have an input signal which is x of t for the continuous time case, and x of n for the discrete time signal. So if the input is equal to, for example, e power st for the continuous, then the output is h of s times the es times the input signal. Similarly, for the discrete time signal, if the input is z of n, then output is h of z times z of n. So that means whatever we give at input, we get some uh, scaled version of that input at the output. So this scaling factor or scaling amplitude denoted by h of s for the continuous time case and h of z for the discrete time case will in general be a function of complex variables, right, s or z. So you can note that you can notice that the whatever you give it at the input, you get the same at the output. So we can say we get amplified or scaled version of the input. So for a signal, if a signal for which the system output is possibly a complex times the input is called the eigenfunction of the system. So such a signals are called the eigenfunctions of the system. So you maybe know that eigen means the same. So whatever you give at input, you get the scaled version of that. So that's why a signal will be called eigenfunction of the system if you get the scaled version of that signal. The amplitude factor is called the eigenvalue of the system. So in case of the Fourier, h of s or h of z will consist of imaginary part only. You understand h of s or h of z are the uh, complex numbers. So like we have done this, that s equals to, maybe it doesn't look very, because it's difficult to draw with the uh, mouse, but anyway, this is something like j omega for the continuous time case, s equals to j omega. So that means if omega equal sigma, right, if sigma this is equal to 0, so in that case the complex number s reduces to j omega. So in case of Fourier, we will have j omega, and this complex amplitude factor will be called as the frequency response of the system. So to show that the complex exponential signal are indeed eigenfunctions of the LTI systems, so let's consider a continuous time LTI system with impulse response h of t and input signal x of t, such that x of t equals to e power minus st. So in that case, y of t will be equal to x of t convolved with h of t, or h of t convolved with x of t. You have done the commutative property, so you understand that the convolution operation holds the property of commutative. So that means it's up to you. You convolve h of t with x of t, or you convolve x of t with h of t. So mathematically it can be written as y of t equals to summation integration from minus infinity up to infinity h of tau x of t minus tau d tau. Now because x of t equals to e power st, so that means x of t minus tau will be equal to e power s and t minus tau. So it can be split, okay, so because it was, so h of tau e power st minus s tau and d tau. So if you look at, then we can split it into e power st times e power, right, times e power minus s tau. So because the integration is around the tau, so that means e power st, because neither s is involved here nor the t is involved here, so we can take them out. So it is left with um, e power st taken common, so we are left with this one, h of tau minus e power minus s of tau d tau. So that means if we represent h of s, the system response or the uh, complex amplitude factor by h of s, then we can write y of t equals to h of s times the e power st, which is input. So the output is basically h of s times the input. So you can see that we have shown that complex exponentials are eigenfunctions of the LTI system, right? Because whatever you give at input, you get the same, but it's scaled version. So here we have the comparison of not comparison exactly, but how the continuous time and discrete time differ. So we have here the input signal e power s of t, so the output is s of t times h of s, which is a complex amplitude factor or complex scaling factor, and h of s for the continuous time is when we take the multiply the impulse response with e power minus st and then integrate it, and then we using limits of minus infinity up to infinity, we find the complex scaling factor for the continuous time case. Similarly, in discrete time case, input signal is z of n, right? So these all are valid only when we have the input signal in terms of complex exponential signal, right? So you can easily observe that when the input is complex exponential signal, the output is simply the response or the scaling complex scaling factor times the input, right? If you compare it with the convolution, so you remember we represented for the convolution we represented the signal in terms of scaled and shifted impulses, and once we represent the signal in terms of scaled and shifted impulses, then the output was equal to the convolution of the input signal with the impulse response of the system. So you understand convolution is pretty tedious work. But if we compare with this one, if we represent the signal, if we can represent a signal in terms of a complex exponential signal, then the output is simply the response or the scaling factor, complex scaling factor times the input signal. So that's quite straightforward method, right? Similarly, for the discrete time case, we have if input is z of n, then output is h of z times z of n. And similarly, h of z can be found by summing the the product of impulse response and z power minus k from minus infinity up to infinity. So let's consider an example. We have the input-output relationship as shown here. So that means what the system is doing, system is shifting the input signal by 3 to the right side, or simply we can say the output is the delayed version of the input. So let's find the system response here, or the complex scaling factor here. So the input is x of t, which is equal to e power j 2t, right? So when this is given to the input of the system, then the output is simply shifted version of 8 by 3 units. So that means e power j 2t, we can say that e power j 2t minus 3. So this will be the output, and if I multiply 2 with this, so I get e power j 2t minus j6. Okay, so if it will be something like, so it's something like e power minus j6 if I open the bracket and this, and we can split it into 2. So this is the system response, which is h of s, and this is the input signal. So that means h of s is basically equal to e power minus j6. So s here is j2, right? You understand, because in general we have x of t equals to e power st, right? So if you compare this with this, so that means s basically equals to j2, right? So that means s of j2 equals to s equals to j2, and the real part of this s is basically 0. So h of j2 equals to e power minus j6. So this is how you found it. You can also find it using the equation or the formula, which is h of s equals to summation integration minus infinity up to infinity, and h of tau multiplied by e power minus s tau d tau, right? So to use the formula, first we need to find the h of tau, or impulse response. So how to find the impulse response? That's very simple. You say what is impulse response, and we say impulse response is basically output of the system. So output of the system, this one. So output of the system, we represent h of t. And what is impulse response? Impulse response is the output of the system when input is impulse. So I replace input with impulse, so it will be impulse of t minus 3. So this is the impulse response. If I integrate it from minus infinity up to infinity, and if I multiply it with e power minus st and then integrate it from minus infinity up to infinity, then I'll get the h of s. So by putting value, we can see that minus infinity up to infinity, and this is impulse of tau minus 3, and this is e power minus s tau and d tau. So this will result. Okay, so you understand impulse is 0 from minus infinity up to infinity, except a point where its argument is 0. The point where its argument is 0, it has non-zero value. Okay, so when the argument of this will become 0, it will be 0 at tau equals to 3. When tau equals to 3, this will become 0. So impulse of 0 will become 1, and e power minus s tau, right? So you understand tau is 3, so I can say that this will be equal to e power minus 3s, right? So because the input signal is equal to, right? So you understand from here that s is basically equal to 3. So that means h of h of 2j, right? H of 2j will be equal to e power minus j6. Okay, so I think quite straightforward. So here is another example where we have the same system, that is the delaying system that delays the input by 3 units. Okay, so now the input is something like this and you have to find the output. Okay, so I hope you can do it using both the approaches, so you should try it. Okay, so again, just the repetition that for a signal for which the system output is constant times the input is referred to as an eigenfunction of the system, and the amplitude factor is referred to as the system's eigenvalue. Now you understand that S has value sigma plus j omega, where sigma is the real and j omega is the imaginary value, right? So when when real of S equals to 0, that means we have just the imaginary values S equals to j omega, and in that case we can say e power st basically equals to e power j omega t, and h of S equals to j omega, right? So that's again clearly understood. The system function h of j omega is called the frequency response of the system, right? So the system function or the complex amplitude when the real part is 0 is called the frequency response of the system, or the Fourier. In Fourier we have this situation, right, where the real part is 0 and we just have the imaginary part. So e power h of j omega when real part is 0 has value h of t times e power minus j omega t, and this is called the frequency response of the system, right? So let's have an example on finding the frequency response, right? So this equation you have already gone through and you understand it. I think there's negative sign here, right? So we have this equation which is called the impulse response, and we have to find the frequency response. You understand frequency response is same as the complex amplitude or scaling factor, where we replace s with j omega, right? That is, the real part is 0. So let's find it. So because here we are multiplying with u of t, so that means the lower limit will reduce from minus infinity. Now it will be 0, and we have 1 by rc, which is the scaling, right? And e power minus t by rc, not t, in fact tau by rc, right? So that's tau by rc, and we again have another exponential, that is minus j omega tau, and we have d tau. So that means we can take out the coefficient or the scaling, which is 1 by rc, and we have 0 to infinity. And if I multiply the two, because bases are same and they are multiplied, so power will be added. So taking tau as common, so I will have e power minus tau, maybe we take common. Okay, so we take minus tau common, so this will have j omega plus tau is common, so we have 1 by rc. 1 by rc. Okay, and this is d tau. So integrating this will result into 1 by rc, and this will be something like, the integration of this will be minus, right, j omega. So let's write 1 by rc before 1 by rc plus j omega. You understand it's norm that we write the real value first and then we write the complex one. So we have this, and here we have, if I put the limits, right, it is something like okay, so when I put the limit here, so the upper limit is infinity, so it will be e power, right, minus infinity. So e power minus infinity is basically 0, right? Then again, if I put the lower limit, so lower limit is 0, so it will be e power 0 is 1. So I get something like, so we have, so when we put minus infinity, you understand here is minus sign here, so e power minus infinity will be 0, which is here, and we have 0, so e power 0 is 1, so which are written here, so 0 minus 1, right? So we can cancel this minus with this minus. Also, I've taken out minus, not minus, 1 by RC from here. So if I take 1 by RC from here, I will be left with 1 here plus j omega RC. So you understand, if I move it again in, so here we'll have 1 by RC, and here we have 1 by RC, and RC they will cancel, so we have j omega. Okay, now this 1 by RC cancels with this 1 by RC, so that means I get h of j omega, h of j omega equals to, so this is the frequency response we have found. You understand, we call it frequency response because the real parameter of s equals to 0 and the imaginary part is just j omega. So j omega is the frequency, so we call this the h of j omega as frequency response. So you can see that frequency response is basically a complex. Complex means that it has a real part and the imaginary part. So if we have something complex, then so the frequency response which we have just found is complex. So when something is complex, it has magnitude and phase representation. So let's see how we can, what is the frequency response of this circuit. The frequency response, not frequency response, magnitude response and phase response of the circuit. So magnitude response is basically a graph that shows magnitude versus the frequency. Frequency is plotted on the x-axis, whereas magnitude is plotted on the y-axis. So it can be seen from, it can be noticed, I mean, that the independent variable in this case will be the frequency, which is omega. So let's find the frequency response, a magnitude response first. So we have found that h of j omega equals to 1 over, so you understand, this is 1 over j omega RC, so the magnitude will be h of j omega absolute value, and this is equal to real square plus imaginary square whole square root. So real is 1, 1 square is 1, and omega RC square, right, and whole square root. So to plot the magnitude response, we'll take three different frequencies, that is omega equals to 0, omega equals to 1 by RC, and omega equals to infinity. So the same for the negative frequencies, that negative for 0 is same, but for omega equals to minus 1 by RC, because we are taking square, so that means either frequency is negative or positive. In both cases we have the same value, so that means the magnitude response will be symmetrical about the 0, or we can say that magnitude has the even symmetry. So when omega equals to 0, RC multiplied by 0 will result into 0, 1 over 1 plus 0, it will be 1, and square root of 1 will be 1. So at omega equals to 0, frequency response, the magnitude response equals to 1. Now we take omega equals to 1 by RC. So when omega equals to 1 by RC, in that case, you can see that this is RC multiplied by 1 RC, 1 over RC, it will cancel and we'll have 1 here, right? So that means we have 1 over 1 plus 1 by RC times RC whole square. So you understand if omega is frequency is positive or negative, because it's squaring here, so that means we get the same value. So this is something 1 over 1 plus 1 square root, so it will result into 1 over square root of 2. Similarly, the third point is when omega equals to infinity. When omega is infinity, in that case you can imagine that infinity multiplied by RC will result into infinity, 1 plus infinity will result into infinity, square root of infinity is infinity, and 1 over infinity will be 0. So that means h of j omega, j of infinity, it will be something 1 over 1 plus infinity into RC. So I hope you understand this will result into 1 by infinity, and 1 by infinity is basically 0, right? So if we plot the graph, it will be something like this one x-axis, exactly this one. So here at 1 by RC, the magnitude will be 1 over square root of 2. Okay, similarly for the negative case, because we are taking here square, so whether frequency is positive or negative, in both cases we get the same answer. So it will be 1 over square root of 2. Okay, so you can easily observe that as we move from 0, at 0 it has maximum value of 1, the frequency response has maximum value of 1. So when you move from 0 in either direction, either positive or negative, basically the frequency the magnitude is decreasing. So that means for higher values of frequency, the magnitude of this response will be very, very low. So that means when the input has high frequency, the output will have value very small, because input and output are related by the expression y of t equals to h of j omega times the input, right? Complex exponential. Input must be in the form of complex exponential. So as frequency increases, the value of this decreases. That means for higher frequency, output will decrease, whereas for low frequency it will have a high value. So it's similar, or exactly the low pass filter. So let's find what is the phase response of this. Now to find the phase response, you understand how do you find, for example, you have a complex number z such that z equals to a plus j b. So phase of this will be equal to tan inverse imaginary is b, right? So tan inverse b over a, right? So for the case of frequency response, we have h of j omega, and this is equal to 1 over 1 plus j omega RC, right? So for the case, because now we have a fraction, right? So in this case, we have the phase equals to phase of the numerator minus phase of the denominator, right? So let's represent it by angle h of j omega. So angle h of j omega will be equal to tan inverse. If we look at the numerator, so here we have imaginary part 0, so that means 0 or 1 minus, because this is denominator, so the phase in the denominator is negative, so that means minus tan inverse of what is the, so this is the imaginary, so imaginary omega RC divided by real, so real is 1. So because in this case, if you look at this one, this is tan inverse of 0 or 1, so it will be 0, so that means it is 0 0, right? So the phase of numerator will be 0, whereas phase of denominator equals to omega R C. So again, we consider 3 points when omega equals to 0, right? We have 3 points to, so A is when omega equals to 0. In that case, angle of h of j omega equals to 0, right? The second is when omega equals to plus 1 by RC for positive frequency, and for negative frequency minus 1 by RC. So in that case, if you look at this one, omega and RC, they will cancel, you get 1, so you have tan inverse of, remember this is 0, so and minus, right, because 0 minus tan inverse omega RCS will be RC omega RC will be minus tan inverse omega RC, because, right, so tan inverse of 1 by RC, and this is also RC, so RC cancels with RC, this is 1 by RC, and this is RC, so RC cancels with RC, so you get 1. Tan inverse of 1 is basically how much? Pi by 4. Okay, so this will be, minus is already there, so it will be pi by 4. Similarly, for the third case, we have omega equals to infinity, right? So that means angle of h of j, right, and infinity, this will be equal to minus tan inverse of infinity, right? You understand, because infinity multiplied by RC will result into infinity, and tan infinity is basically minus pi by 2, right? So similarly, you go for the negative frequency. So for negative frequency, you have 0 is same, but part B, we have 1 by RC, so negative frequency will be minus 1 by RC. Again, here we have infinity, so it will be minus infinity. So you'll find that for the, when frequency is negative, phase is positive, and which we have already found that when frequency is positive, phase is negative, that is 0. Then we have minus pi by 4, and then we have minus pi by 2. So this is the point where we have 0. Then at this point, W equals to RC, and then at infinity, right? So we can, combining these points will give us the frequency phase response of this system. And remember, what is a phase response? Phase response is a plot or graph of the phase versus the frequency. On x-axis we have the frequency, whereas on the y-axis we have the phase value. So you should go for the negative values also and verify these. Okay, so I think that's all for today. So see you in live session. If you have any question, we can discuss.